IIT Kanpur, and then he did his postdoc from Ohio State University, and he was a guest lecturer in IIT Kanpur, and he has also served as an assistant professor in IIT Jammu, and finally he is now in IIT Dhanbad, and he is very much his work is very much well known for the research in turbulence related fields. And I hope today we'll be having a very interesting talk on the dynamics of the spatio-temporal wavefront as unique precursor of the flow transition. So without the further delay, I hand over the session to Professor Swagata. Please continue.
Okay. Okay. Thank you, Chandan, for such a warm welcome. So let me begin. So basically my talk is on the as Chandan said, it is basically on the dynamics of the spatio-temporal wavefront as a unique precursor of flow transition. So I will be basically discussing slowly, and if any of you has any question or doubt, you are always welcome to just unmute yourself and ask me the question. So I'll be very much happy to answer your question. So I will begin my talk first by giving a small introduction of laminar turbulent flow and what do you mean by laminar turbulent transition, the basic ideas behind the instability, and also another term which is basically called the receptivity. So as you know, and any undergraduate fluid mechanics student will know, basically the laminar flow is characterized by some sort of orderly flows where the fluid particles follow the smooth paths in layers, where each layer is basically moving smoothly past the adjacent layer to little or no mix. In contrast, so in comparison to the laminar flow, we also have another regime of flow which is called the turbulent flow, and these turbulent flows are essentially chaotic in nature in the sense that there is some kind of a pseudo-random fluctuation in the flow variables, and also, as you know, the flow undergoes intense mixing in contrast to the laminar flow. Say, just to give you some kind of example, say I'm basically collecting these figures from the internet. So this is a plume from an ordinary candle. So, and this picture has been collected from this source, this Wikipedia. And as you can see, basically in the lower part, the plume is much more orderly in nature. Okay, so and as it rises up, then there are some kind of undulations and oscillations, and in later part, these oscillations basically intensify, and then finally a kind of a chaotic or basically the turbulent flow is noted. So this is so in the bottom part the flow is laminar, and in the top part the flow is basically chaotic. Flow is basically chaotic or turbulent. Okay, so in between the laminar to turbulent flow, so there is the transition from the laminar to the turbulent flow, and here our effort is basically to understand one of the precursors of this laminar to turbulent transition, and to show this chaotic or the pseudo-random fluctuations in the turbulent flow. Here I am showing you just another picture which I have obtained from this URL, which essentially shows the laser-induced, basically the laser-induced fluorescence image of an incompressible turbulent boundary layer. Okay, and then so in comparison to the laminar flow, basically in the turbulent flow we have a very the turbulent flows are essentially very chaotic in nature. There are sort of you can say pseudo-random fluctuations. So I am using this pseudo because you cannot exactly call these fluctuations as the random fluctuation, as these are basically governed by the fluid dynamical equation. Okay, and similarly, suppose you have a flow past an angle of attack, flow past an aerofoil at a certain angle of attack. So in the top part, in the initial part, the flow is orderly, and from this orderly part, and you can see basically at the later part, the flow becomes much more chaotic in nature. Much more fluctuations are observed in the flow, and so from this laminar to turbulent flow, so from this laminar to turbulent flow, so there is an inherent there is essentially transition. This uh, this transition is happening at some particular point, and similarly for this jet, which has this picture has been taken from this paper. Okay, so here is also another example of the so this jet near the exhaust is laminar in nature, and as it basically proceeds or proceeds forward, there are some kind of instabilities, and these instabilities gradually intensify, and ultimately the laminar to the turbulent transition takes place. Now, generally, often the question is asked, which one is better, laminar flow or the turbulent flow? Just to say that, I mean, there is a definitive answer to this. So, say for example, take the example of this flow past an aerofoil. Turbulent flow. So obviously, if you have a turbulent flow, for the turbulent flow, the velocity profile is fuller, and therefore the skin friction drag will be high. But also this basically leads to the this also basically leads to the reduction in the pressure drag. Okay, and also in the case of this jet flow, this laminar to turbulent transition is basically leads to enhanced mixing. So there are different regimes. So in certain regime, in certain design condition, you might prefer a laminar flow, and in certain design condition, you might prefer a turbulent flow. So basically depending upon your requirement. And then comes the question, what are the factors affecting the laminar to the turbulent transition? So there are various approaches. There have been various studies, experimental studies, numerical studies, and also the theoretical studies as well. So regardless of the numerous theoretical, experimental, as well as the numerical studies, there are several aspects of the laminar to the turbulent transition in the fluid flow which still remains ambiguous. I mean, there are several more open questions. So I just write these two lines just to highlight the importance of the turbulence flow. So importance of the turbulent flow, just to amplify the point that in the Feynman lectures, the turbulence is noted one of the unsolved problems in the classical physics. So the features of the turbulence, whether it is stochastic or whether it is deterministic in nature, so there are several open-ended questions, and I mean the complete nature of the turbulence as well as the laminar to the turbulence transition is there are several open-ended questions. And here I quote one of the quotation by the famous fluid dynamicist Horace Lamb. So all of you might have read the classical book of Sir Horace Lamb, and here so I have basically come across this quotation, and I have just put it in the slide. So he basically said in one of the meeting of the British Association for the Advancement of Science that I am an old man now, and when I die and go to heaven, there are two matters on which I hope for enlightenment. One is the quantum electrodynamics, and other is that other is the turbulent motion of fluids. And about the former, I am rather optimistic. So he himself is saying that he is rather optimistic that in future he might be able to understand the quantum electrodynamics. However, the turbulent motion of the fluids will still remain unsolved. So I mean, so this basically highlights that the difficulty or the complexity of this particular motion, this difficulty or the complexity of this turbulent motion in general. So therefore, our effort here is basically in determining one of the unique processes of flow transition and its subsequent dynamics. So here we are trying to basically try to shed light in one of the aspects, in one of the unique process of flow transition and how it is happening for a particular deterministic case. Okay, so before starting, so let me for the audience give a little introduction or the background in what do we actually mean by the stability or instability. So here in the stability or instability, the fundamental question is regarding the base flow. So you have the fundamental idea is that suppose you have an equilibrium flow, and if you perturb or disturb that equilibrium flow by some sort of infinitesimally small disturbance, so the disturbances are much smaller in magnitude than the magnitudes of the equilibrium or the base flow, and then it is to be determined whether these infinitesimally small disturbances grow or decay. So if the disturbances grows, then the initial set of growth will be determined by the linear instability mechanism. So in the linear instability mechanism, will basically predict some kind of primary amplification. And the basic idea is that after the primary amplification, we'll take the disturbances to a limit when the disturbances will, the primary linear amplification will basically take the disturbances to a limit when the disturbances will no longer small with respect to the base flow, and then the subsequent growth of the disturbances will take place by some sort of secondary or nonlinear growth stages. So this is the general understanding as far as the stability or instability of the base flow is concerned. So obviously, if the disturbances decay, so obviously if the base flow is stable, so here that idea of stability basically kicks in. So if the base flow is stable, so for any infinitesimally small disturbance, if you give any infinitesimally small disturbance, so the amplitude of the disturbance will, with respect to time or space, will basically decay, and the steady base flow will again revert back to its original states. Okay, so this is the general idea for the as espoused by the people who generally practice the stability or instability route of understanding or explaining the fluid flow transition. And then there is another viewpoint. The other viewpoint is that so the basic idea in the basically in the stability or instability is that if you have a base flow, you try to characterize the properties of the base flow. You try to find out whether that base flow is stable with respect to some sort of infinitesimally small disturbances or not. And there is a counter viewpoint. The counter viewpoint is I will have the base flow, and then I will basically perturb that base flow with respect to some sort of deterministic excitation, with respect to some sort of excitation which are real in nature, which are physical in nature. Say, for example, I am showing you basically this schematic diagram for flow past an semi-infinite flat plate. So here you have an uniform flow, and we have this boundary layer. This boundary layer is basically growing. Now, this flow situation can be subjected to various sort of disturbances from the free stream as well as from the wall, as well as from the flat plate. So what are the disturbances that might appear? We might be having some kind of excitation from the wall. I have denoted it by here this A. So there might be some kind of excitation by the wall, some kind of vibration from the wall. If some part of the wall is flexible in nature, then the wall might not be entirely smooth. So there might be some kind of roughness effects. So those will essentially disturb the flow. And then there might be some kind of disturbances from the flow as well. Say, for example, there might be some kind of convecting vortices in the free stream. Say, for example, the wing in the vicinity of a propeller, and the propeller will basically shed some kind of helical vortices, and these helical vortices will either they might go and strike the plate, or they might flow above the plate, and as they will basically move above the plate, so they will be essentially disturb the underneath boundary layer, and those disturbances might grow, and then ultimately some sort of transition from the laminar to the turbulent stage might be happening, and then you might be having some kind of fluctuation from the mean flow itself in the form of the Phys turbulence, say small vortices uh, in the oncoming flow. Then you can have some sort of acoustic perturbation or any other form of radiation. Okay, any other form of thermal radiation as well. So you can also have some sort of thermal disturbance. So there are various factors, various extraneous factors which affect how that basically determine how this actual transition is happening, and that process, so that process of encountering what is the actual cause of the perturbation and what is actually giving. So this is essentially basically treating the fluid as a dynamical system point of view. So here we have a dynamical system. We give some specific input in the nature of this basically this definitive excitation, and how the dynamical system is essentially responding to these given perturbations, and whether those perturbations are growing or decaying. So that picture is essentially clubbed, and that is called the receptivity mechanism. So we have an instability approach and we have a receptivity approach. So here we take the receptivity approach. We give a very definitive excitation from the wall to the boundary layer, and we try to find out what kind of disturbances it gives, what kind of say I am schematically showing some kind of waves. So what kind of disturbance waves or the wave packets, so they might bounce. So what kind of disturbances or disturbance wave packets that might generate, and whether these disturbance packets, what are the essential dynamics of these disturbance packets, and how these basically grow or decay, and how this basically essentially determines the eventual transition process. So that is what we here basically try to find out. Okay, so before moving, so this is a block diagram I am showing here. So basically for this, basically for the dynamical system point of view, so we have a we consider the fluid as basically a dynamical system, and we give some kind of input disturbance. So that might be some kind of background disturbance or some kind of imposed disturbances, and then we have this process called receptivity. How this is the process. The receptivity is essentially determines how how the system is basically responding to this imposed or the background disturbances, and then you can have either the classical or the conventional mechanisms where you have some kind of viscous tuned wave packets. They might be the spatial temporal in nature. So spatial is, that means it is essentially growing with respect to the space, and temporal means it is essentially growing with respect to the time. Okay, and then you can have the spatio-temporal wave packets. So the wave packets which essentially moves both in space and is also grows with respect to time. So the movement cannot be described only by the spatial coordinate or by the temporal coordinate. So this is essentially the spatio-temporal in nature. You have to consider both the space and time, and then you have some kind of bypass mechanism. So in the bypass mechanism, the conventional idea is basically that where you will not get a similar sort of viscous tuned wave packets. But obviously this is not true. So you have a essentially I hope the Aditi is also there in the audience, and she has done the simulation for when the boundary layer is excited by a single Phys convecting vortex, and she has noted some kind of disturbance packets or the spatio-temporal wave packets being generated for that. So therefore, I mean, it is not always possible to bifurcate in this current basically in this current route. Okay, so this bypass mechanism, this route might be due to some kind of surface roughness effects or some kind of free stream turbulence or any other form of excitation from the free stream. And then we have the secondary or nonlinear instability phases or the later stages of the transition, and then the final output is essentially the turbulence. Okay, so therefore our idea is that it will essentially follow this kind of flowchart. Okay, essentially follows this kind of flowchart. So so this is the general picture, and then
Hi, Swagata, can I interrupt you a bit?
yes, sure.
Sorry, I mean, I thought that it could be relevant. I mean, how do you see the dynamical, local, or global bifurcations route to be, which can be, equivalent to this conventional or classical mechanism? Do you see any relevance between them?
Yeah, so so the in the global stability analysis, so you have only basically the disturbance evolving with respect to the time only. So the idea is that you have some disturbance which are unstable with respect to time, and then in later stages, if the amplification rate is much higher, so then that will lead to some kind of breakdown and some kind of transition. And in the local sense, maybe our it might be some kind of this spatio-temporal wave packet or this spatio-temporal wave front. So you have a packet, you have a bound packet, and then as it basically moves in space, it also grows with respect to time. So so I think say for example, the global scenario is generally noted, for example, for the internal flow. Say for example, flow in a lead-driven cavity, or say it can, or maybe in the scenario of flow past a circular cylinder. So you have basically the vortex shedding. So maybe at some higher Reynolds number, the vortex shedding, which is which is basically a manifestation of the instability. So that might lead to some kind of bifurcation. Okay, so I mean the point that I wanted to make was that, so say for example here we can say for a flow past a flat plate we can have basically this kind of routes. For other flow scenarios, you can have the other mechanisms as well.
Sure, sure. I get that point that here it is not only temporal, the spatio-temporal characteristics are very important.
Yeah. So it is spatio-temporal. So that means you cannot exactly basically determine it by the spatial or the temporal mechanism. So it is both space and time which you have to essentially consider.
Yeah, please continue.
Okay. So before moving, okay. So here our main focus is on this spatio-temporal wavefront. Okay. So before moving forward, so for the audience, so let me give a brief description of the instability analysis. So I think it's a little bit of fundamental. So if you already know, I think most of you already know, but those of you who do not know, so basically let me give this brief description on this instability analysis. So I will consider again a flow past a flat plate. Okay, so if we consider the 2D incompressible constant density boundary layer, so we have the governing equations as basically the continuity equation, which is del dot V is equal to 0, and the momentum equations. And here we are not considering the energy equation because the flow is incompressible with a constant density, and we are also not considering the temperature effects. So if you have the temperature effects, you might as well as also include the equation. You might as well as include the equation for the temperature, and then The basic idea in the instability analysis is that you basically decompose this governing equation into the equilibrium flow as well as for the disturbance flow. So any flow variable we essentially decompose it as a summation of the time invariant mean quantity and mean quantity which is not fluctuating with respect to time. So if there are analysis when the mean quantity also is a function of time, and for that you can basically give some kind of Floquet type of analysis. So we are not here basically considering that. So any flow variable is decomposed as a summation of the time invariant mean quantity and corresponding disturbance quantities. Okay, so and then we'll basically substitute it in these governing equations, and we'll try to linearize the equations, assuming that the disturbance quantities are much order of magnitude smaller than the time invariant mean quantities. Okay, say for example here we will substitute the u component of the velocity, which is small u, as a summation of the base flow, which is capital U plus epsilon u prime, where epsilon is a very small quantity, epsilon is much smaller than 1, and u prime is essentially the disturbance quantity. So we can basically separate. We have here basically two terms. One is of order 1, another is of order epsilon. Similarly, the V can be written as a summation of capital V plus epsilon V prime, and the pressure is the capital P, which is the mean pressure, plus the epsilon times P prime. So the P prime is basically the disturbance quantity. And suppose we make the parallel flow approximations. So the parallel flow approximation is that we assume that whatever the profile we have at a particular station, so that remains frozen with respect to that basically remains frozen. So there are approaches where this parallel flow instability, the stability approximation is violated. Say for example, the parabolized stability equations, or the biglobal or the triglobal stability approaches. So there, this approximation is not basically observed, and there however the basically computations become much more complex. So without basically moving into that complexity, let us assume that this parallel flow approximation holds, and under this parallel flow approximation, the base flow u is only a function of the y coordinate, is only a function of the wall normal coordinate y, and the v velocity, the wall normal component of the mean flow, is essentially 0, and also the pressure, the mean flow, the pressure is also a function of y. Okay, so if you substitute that in your governing equations, and from there you try to separate the mean and the disturbance quantities, you will get this following set of equations for the disturbance quantities. Okay, so the first one is the continuity equation, the second one is the momentum equation for the disturbance u component of velocity, and the second one is the momentum equation for the disturbance v component of velocity. Okay, so then the classical approach is that you express this disturbance quantities in terms of the Fourier Laplace transform. Okay, so basically, essentially these are the linear equations. So you essentially take the advantage of this Fourier Laplace transform. So here u prime, v prime, p prime transpose, these are expressed as by this integral. So here alpha is the wave number in space, and beta is essentially the frequency. Okay, so f is the Fourier Laplace amplitude corresponding to the disturbance u velocity, phi is the Fourier Laplace amplitude of the corresponding v velocity, and pi is the Fourier Laplace amplitude corresponding to the disturbance pressure. Okay, and these are, so therefore these are f, phi, and pi are the functions of the y, the wall normal coordinate, and obviously there has to be the functions of the Reynolds number, and the the streamwise wave number alpha as well as the circular frequency beta. Okay, so now here, so here let me point out that this Reynolds number RD, since we are making the parallel flow approximation, so the Reynolds number requires the specification of a suitable length scale, and since we are making the parallel flow approximation, the suitable length scale here is essentially the displacement thickness, that local displacement thickness. So this is the Reynolds number is essentially based on the local displacement thickness. So in some of the slides, so I will also write it as RE subscript delta star, where delta star is the displacement thickness at that particular location. So if you substitute this in this disturbance equation and try to simplify it, you will get this following ordinary differential equation. And this ordinary differential equation is called Orr-Sommerfeld equation. Okay, and as you can see, this is essentially a fourth order equation where this capital D is nothing but capital D is nothing but the d dy. Okay, so we have this Orr-Sommerfeld equations. Now for the stability analysis, we assume that there is homogeneous boundary conditions for the disturbance quantities at the wall as well as at the phase stream. So the disturbance v velocity components, and phi prime is essentially the disturbance u velocity component. Why? Because if you substitute it here from this equation, you can show that phi prime essentially represents the disturbance u component of velocity. So for the stability analysis, we use that the boundary conditions are homogeneous. So that is the essential idea of basically the stability analysis. You have the governing equations for the disturbance, and then you use the homogeneous condition, and then you try to find out the eigenvalues. So those eigenvalues basically determine whether that particular flow is stable or not. So the idea is essentially same with respect to the here, as well as if you go to the some higher order version which is more computationally intensive, say for example the bi-global or the tri-global type of analysis. Okay, so phi 0 is equal to 0 and phi prime 0 is also equal to 0. So that means the disturbance v as well as the disturbance u component velocity is at 0. And obviously, since it is an unbounded external flow, we also expect that the disturbance quantities decay in the phase stream. So both of the disturbance v as well as the disturbance u components decay in the phase stream. So okay. So now this Orr-Sommerfeld equation, you might say this is an ordinary differential equation, and you have various numerical algorithms to solve this ordinary differential equations. But the problem with the Orr-Sommerfeld equation is that it is a stiff differential equation. So it is not very possible to numerically solve this Orr-Sommerfeld equation by using the conventional numerical algorithms like the Runge-Kutta method. So you have to have some sort of special treatment, and the compound matrix method is one such method. So anyone, if you want to read much more about the compound matrix method, you can read basically these two following references. Okay, so moving forward, so as I noted here, for this particular flow problem, the Orr-Sommerfeld equation is a fourth order stiff differential equation. If you add the heat transfer part, you can also have an analogous Orr-Sommerfeld equation considering the heat transfer, but then that becomes a sixth order stiff ordinary differential equation. If you add the compressibility part, the order becomes even higher. It becomes an eighth order system. Okay, so now considering if the Orr-Sommerfeld equation is a fourth order stiff differential equation, so since this particular equation is in fourth order ordinary differential equation, it will invariably have four modes. Say I represent it by phi 1, 2, 3, 4, and all is a function of y. Now here it can be shown that out of these four modes, two modes essentially grow in the phase stream, and essentially two modes decay in the phase stream. So suppose phi 1 and 3 are basically decays in the phase stream, and phi 2,4 basically grows in the free stream. So obviously, for the stability analysis, you only have to retain the modes which essentially decays in the free stream. So therefore, phi y can be written as a linear combination of phi 1 and phi 3, which basically decays in the free stream. And you impose the other boundary condition and the wall, and from there, you can basically remove the arbitrary constants a1 and a3, and you get only one equation in terms of the phi 1, phi prime 3, all evaluated at y is equal to 0 at the wall, and this following condition has to be satisfied, and this is basically the dispersion relationship. Why it is the dispersion relationship? Because this relationship basically dictates a relation between the streamwise wave number alpha and the frequency beta. Now, so therefore, any relationship which gives you an equation with respect to the streamwise wave number, with respect to wave number as well as the frequency, is called the dispersion relationship. And therefore, this is essentially basically is the dispersion relationship, from which you can find out by satisfying this dispersion relationship, you can find out the conditions for the stability. Now, there are various approaches for the instability analysis. The common approaches are either spatial instability or.
May I ask a doubt?
Yes.
No, some basic doubt, because in the earlier slide you showed you are keeping only the decaying modes, right?
Yeah.
Why is it so? I'm just interested here.
I am keeping the decaying modes because if the modes basically grow in the free stream, so these are basically unphysical in nature, right? The disturbance cannot grow in the free stream. Disturbance has to decay in the free stream.
Okay.
If there is no excitation from the free stream, there are kind of modes which also grow in the where the which essentially do not basically decay in the free stream, and those kind of modes are basically the continuous spectra. So those are treated when theoretically people try to find out the effect of the free stream turbulence, which basically flows above the flat plate. Okay, so now here, suppose here you only have an excitation from the wall, or you are interested in a nature where basically the disturbance, the source of the disturbance is basically closer to the wall. So then you expect that the disturbances will essentially decay when the y becomes larger. So therefore, you don't consider those modes.
Oh, okay. Thank you.
So, sorry, we have a follow-up question here. That are these decaying modes chosen based on boundary condition and later corrected?
These.
I think the audience this question came. You can unmute and ask if you have more doubt.
Yeah.
So the main question is: are these chosen based on boundary condition?
So basically here in the stability analysis, we are assuming that there are no, the stability analysis is different from the receptivity analysis in that basically in the receptivity analysis, there is a definitive excitation. Okay, so if you have a definitive excitation, so I'll also explain the receptivity part. So if you have a definitive excitation, then these conditions, you cannot satisfy this homogeneous condition. These homogeneous conditions, these conditions are imposed such that you can find the modes of the system. You can find out the eigenvalues of the system. If there is some kind of inhomogeneity, suppose you have an inhomogeneous, inhomogeneous part. So then the actual solution you have to write with respect to the, as you know from your differential equation, you have to write it as a summation of the solution corresponding to the corresponding to the homogeneous equation as well as the particular integral. Okay, so that homogeneous part essentially gives essentially the modes of the system. Now here the stability analysis, that is the idea. So you want that disturbances are, there are no disturbances not given from the wall as well as the disturbances which essentially decay in the system. So if there are some kind of inherent mode, the inherent non-trivial solution, now whether these non-trivial, when these non-trivial solutions are excited and when whether they grow or decay. So, are you satisfied with the answer or?
Yes, I think we can again continue the discussion at the end. Please continue.
Okay, yeah. Uh, so here I was basically talking that. So now the approach generally is adopted whether these instability mechanisms are special in nature. So mind it here, so alpha is the wave number and beta is the frequency. Now, as per the Fourier Laplace transform, the alpha and beta both can be complex numbers. Okay. Now, suppose in the special instability approach, the alpha is treated as basically as a complex number, while the frequency beta is treated as a real number. And then you try to satisfy the dispersion relationship. You try to find out the modes which essentially grow with respect to space. So this is the spatial instability analysis. Whereas for the temporal instability analysis, you take the alpha to be real and the beta, the frequency, to be a complex quantity. So beta is essentially beta is equal to beta r plus I beta I. So depending upon the sign of the beta I, those signals will essentially grow with respect to time or not. Now, if I point out the basically the biglobal or the triglobal type of analysis essentially assumes that essentially assumes the temporal instability of the system. Okay, so and for example, and for the case here, for the slope of the canonical slope of the flat plate, generally the spatial instability approach is adopted, but there is an inherent connection with respect to the spatial or the temporal instability analysis. So with respect to the neutral curve. So I'm basically describing the neutral curve. I'll come into that point. So, so for the spatial instability analysis, so the wave number alpha is essentially a complex number. So alpha is equal to alpha r plus I alpha I. So therefore, since it is e to the power I alpha x, so the disturbances will grow spatially if alpha is negative, and it will decay with respect to the space if alpha I is positive. And with respect now, suppose you take you basically in the parameter space. So here your parameters are the Reynolds number, alpha and beta. Now you can fix the beta to be a real quantity according to the spatial instability analysis, and for every real beta naught and RE delta star, since Reynolds number is defined with respect to the displacement plus delta star, you can find out the exact values of the alpha. So exact values of alpha will satisfy the dispersion relationship. Now, this is the zone. So this is the curve here. This is the red curve, and beyond this zone, alpha I is basically positive. So these signals are spatially stable as per the spatial stability analysis. Whereas inside this curve, the alpha i's are essentially negative. So this curve is called the neutral curve. Okay, so on the neutral curve, alpha I is essentially zero. So if you have a signal, so the basic idea is that if you have a signal, if you excite some kind of disturbance in the boundary layer at a certain frequency, it will spatially grow or decay where exactly your beta naught is located, where exactly is your beta naught is located with respect to that particular RA delta. So suppose your RA delta star value is is equal to 1000. So if your beta naught is below the point corresponding to the neutral curve, then the signals will be basically spatially stable. If it is inside this curve, it will be spatially unstable, and if it is outside, it will be again spatially stable. Okay. So now the actual case, for an actual disturbance, obviously there is no such restriction. I mean, you cannot basically determine whether the disturbances will be spatial or temporal in nature. So it can be spatio-temporal. So that means both alpha and beta can be complex numbers. Disturbances can grow with respect to space as well as time. So that is the spatio-temporal instability analysis. But since it is more computationally intensive, so generally this kind of approach is the spatio-temporal instability analysis is not performed. Okay, so this is all about the instability analysis. So is there any question so far? Then I will try to explain what do you actually mean by the receptivity analysis. So is there a question so far?
I don't think so. Yeah, we can take up at the end. You can continue.
Okay. Okay. So if I plot the basically the mode shape, so here I am taking a couple of figures from my PhD thesis. So this is corresponding to the Reynolds number 1000 and beta naught, the non-dimensional the, the non-dimensional frequency of 0.1, and this is the mode shape corresponding to the disturbance v velocity. As you can see, it is essentially decaying in the phase stream, and this is the mode shape for the disturbance u velocity, and you can see there are basically two extremas. So the one extrema is basically close to the wall, which is called the inner maxima, and another is close to the edge of the shear layer, which is called the outer layer. Okay, so this is the corresponding mode shape. Okay. So now moving to the receptivity analysis. So the whatever I described so far was corresponding to the stability analysis. So this is the stability analysis has to be performed corresponding to homogeneous boundary conditions. But in an actual scenario, you give some sort of excitation. That is the receptivity analysis. You give some sort of perturbation. Okay, so uh, let us move from the stability analysis to the actual receptivity calculation. So in the receptivity problem, we consider the response of a system uh, 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 when there is a definitive excitation given to it. Suppose we are talking of some sort of wall excitation, Now, if there is some sort of wall excitation, obviously the boundary condition will not be homogeneous. Since there is an excitation from the wall, so the other end of the condition that you expect the disturbances to decay in the phase stream, but obviously since you are giving a particular excitation from the wall, so the boundary condition will not exactly be homogeneous. So it will be inhomogeneous in nature. So the specific nature of phi 0 depends on what kind of excitation you are giving from the wall. Okay, so exactly what kind of excitation you are basically giving from the wall. Say for now to find out the actual disturbances, how these actual disturbances are evolving in this particular scenario. Suppose you solve the Orr-Sommerfeld equation corresponding to this inhomogeneous boundary condition. So you get the phi. Okay, you get the phi as a function of the wall normal coordinate y. So from there, if you want to get back to the actual disturbance, so you have to evaluate the integral. You have to evaluate the integral, which essentially we basically defined it here. So and this is called the Bromwich integral. So this is some kind of an inverse Fourier transform, inverse Laplace transform. So you have to do this Bromwich contour integral, and there you have to find out the exact Bromwich contour. Say for example, suppose with respect to alpha, so you have to find out a typical strip of convergence, and accordingly you have to take the Bromwich contour in the in the alpha plane such that it lies in the strip of convergence, and all the poles, since this is a complex equation, it will have some kind of poles, and the poles which basically propagate in the downstream has to be above the has to be above this chosen Bromwich contour, and the poles which basically propagate downstream has to be below this chosen Bromwich contour. And similarly, you have to choose again the Bromwich contouring basically in the beta plane. So the horizontal axis is the real beta naught r. So the real part of the beta naught, and the y-axis is basically the imaginary part of the beta naught. So any of you who which are more interested, so you can basically go to this particular reference and you can know more, or you can also write to me, or you can also the details are also given in my PhD thesis. Okay, so now in the beta plane, the Bromwich contour always has to be taken above the real axis. Why? Because you have to satisfy the causality principle. That basically time always moves from the past to the future. Okay, so you have to satisfy that particular principle. Now suppose you have a very impulse excitation at the wall, and the excitation is at a particular frequency beta naught. Excitation is at a particular frequency beta naught, and this is also localized in space, which is given by this function delta x, and it also has an impulsive onset. So that means it is basically started impulsively. So essentially there was no excitation before t less than there was no excitation before t is equal to 0. There is only excitation only after t is equal to 0. Okay, so that is essentially indicated by this Heaviside function ht. Okay, so that is essentially indicated by this Heaviside function. This is essentially indicated by this Heaviside function h of t. So now you give a very localized time harmonic wall excitation with an impulsive start. So here we are giving a very localized time harmonic wall excitation with an impulsive start. So therefore the disturbance u component of the velocity at the wall is equal to 0. The disturbance v component of the velocity is given by this delta x times e to the power I beta naught t. So since the beta naught is basically the real excitation frequency, and this Heaviside function, as I said, essentially indicates that the excitation has been onset impulsively. Yeah, so this is just an impulsive onset of the excitation. So therefore, as I denoted in the previous slide, the complete free disturbance can be given by this Bromwich contour integral, where this phi of y for this particular excitation, which is localized in space, which is basically time harmonic, and which has an impulsive onset. Okay, so for this particular excitation, the phi y can be given by this particular expression. So here beta is the complex frequency, and beta naught is a real number which denotes your actual monochromatic excitation frequency. So now you can see basically the denominator essentially is basically our original dispersion equation. So therefore, if I write it here, our complete equation can be given by this complex integral here. So therefore, as you can see, all the complex frequencies and wave numbers centered around beta naught are excited. All the complex frequencies and wave number centered around, so you can from this equation you can say that since it has basically the term 1 by beta naught minus beta. So if your particular frequency is closer to the excitation frequency, so its amplitude will be quite higher. So therefore, I essentially write here that all the complex frequencies, since beta can be the complex frequency, and here, so this here we are essentially considering the spatio-temporal receptivity. So therefore, betas and alphas can be complex in nature. So therefore, all the complex frequencies and wave number centered around beta naught are excited, and both alpha and beta are basically the complex number. And it is, as you can see, that this essentially saying that this is basically a linear combination of all the spatio-temporal eigenmodes with a weight which is proportional to 1 upon beta naught minus beta. Okay, so therefore, this Bromwich contour integral method was performed again in this particular reference, and it showed that whenever there was a localized time harmonic excitation, the actual signal at a particular wall normal distance at definitive times. So you can basically find out three distinct part of the evolving disturbance. One part is essentially the local solution at the very close vicinity of the exciter. One part is this asymptotic solution, and you can see here this is basically spatially decaying. So this asymptotic part of the solution are corresponding to the spatial instability modes, which for a flow past boundary layer is also called the Tolman-Schlichting waves. So these are also called the TS waves. So this asymptotic part of the solution basically represent these TS waves. So these TS waves theoretically these TS waves were essentially considered as basically the prime mover for the flow transition. Why? The idea will be, I think, will be clear from the next slide, that it was thought and that whenever these TS waves are spatially unstable and the transition is actually happening because of the spatial instability of those TS waves. Now here we have the authors have chosen the excitation frequency such that it is actually in the stable part of the solution. So if you consider this picture here, the excitation frequency was chosen such that it essentially falls in a part where the flow is spatially stable. So alpha I is positive. So therefore, the TS wave is supposed to decay. So therefore, by the conventional argument, the flow is essentially spatially stable. So even if it is spatially stable, due to the impulsive onset of the excitation, there was a spatio-temporally growing wave packet. As you can see, as I move from t is equal to 640 to 801, there is a spatio-temporal wave packet which essentially grows with respect to space and time, as it is basically propagating downstream, and as it is propagating downstream with respect to the passage of time, it is also, its amplitude is also amplified. Okay, so we see essentially three components of the solution from the linearized spatio-temporal receptivity analysis using the Bromwich contour integral method, and this basically says that that you have to consider the onset of the excitation as well. Whenever you give an excitation, you have to also consider the onset of the excitation as well, and there, due to the impulsive onset, there can be a spatio-temporally growing wave packet. So the even for a frequency case where the flow is essentially stable with respect to the spatial stability analysis. So even for those kind of flows, due to the particular nature of this onset of the excitation, you can have a spatio-temporally growing wave packet, and therefore, since this wave packet was spatio-temporally growing, so you are intrigued and you are trying to find out the further dynamics of this spatio-temporally growing wave packet, whether the growth of this spatio-temporally growing wave packet actually leads to the transition of the flow, and what is actually the role of this spatio-temporal wave packet as well as for this TS wave packet. So TS wave packet, as you can see here, remains spatially bound. So it is consists of some waves. So this peaks is essentially so it is a wave, right? I mean, there is an oscillation, but the extent of the packet remains spatially fixed, whereas the spatio-temporal wave packet moves both in space and time. Okay, so therefore, this linear spatio-temporal receptivity analysis essentially shows that this STWP for the spatio-temporal wave front is growing even if the excitation frequency beta naught is stable. Okay, and so therefore this can be the prime mover for flow transition, but this has to be ascertained from our actual nonlinear Navier-Stokes simulations, and that has been reported in the next slides. Okay, now this is the picture which has been thought to be the, I mean, in all the designs, were to model the transition. This was the classical picture. I mean, you all might have heard about the e to the power n method. So the essentially idea is that now since the boundary layer is growing, the boundary layer is non-parallel. So that parallel flow approximation is not applicable for the boundary layer. So therefore, the displacement thickness of the boundary layer is changing from station to station. So therefore, this RE delta star is essentially changing. Now suppose the basic idea was that, now suppose if you excite the boundary layer at some particular frequency, that will essentially follow this particular ray passing through the origin. And this ray is essentially determines the ray where the non-dimensional frequency f given by 2 pi f nu by u infinity square, where f is the small f is basically the dimensional frequency in hertz, nu is the kinematic viscosity of the fluid, and u infinity is the phase velocity. So this essentially comes by considering that in our previous case we considered the parallel flow approximation. So our essential length scale was the local displacement thickness. Now here the boundary layer is not parallel, boundary layer is non-parallel. So therefore we have to make a switch over from the actual the displacement thickness as the length scale to the actual dimension of the plate, and from there if you do that particular switch over, this you can define this non-dimensional frequency f. So therefore the basic idea was that, so if you have a boundary layer and you excite the flow at a particular frequency, the disturbances will grow and decay following this particular line. So from this excited location to the point where it cuts the lower branch of the neutral curve, which is called the branch 1, the disturbances will spatially decay, and from this point to this point onwards, so the point where this line cuts the lower branch of the neutral curve to the upper branch of the neutral curve, the disturbances will spatially grow, and again the disturbances will spatially decay. So the transition will happen if this growth from the point where this ray intersects the branch 1 of the neutral curve to the point where this ray intersects the branch 2 of the neutral curve, if that amplification is beyond some threshold number, then the flow transition will basically take place, and that is basically the philosophy behind essentially the philosophy behind postulating, suppose the e to the power n method, which is conventionally adopted while designing various aerofoil shapes. Okay, so we will try to examine how this picture is relevant when there is a definitive excitation in the flash plate with a particular onset, because physically this picture is valid when your excitation onset is suppose that t is equal to minus infinity. So you do not consider the effect of the transient, and that problem is called a signal problem. So this picture might be valid for the signal problem, but for a physical scenario when there is an actual excitation, when there is an excitation with a definitive onset, the onset might be impulsive, might be gradual. So we have also showed that even if the excitation onset is gradual in nature, that spatio-temporal wavefront exists, and for those cases also we will try to find out the validity of this picture, and we will try to see that this TS wave packet, this spatially unstable TS wave packet, has a very minor role so far as the flow transition is concerned. It is rather the spatio-temporally evolving, the spatio-temporal front, as we call it the STWF, that plays a much more major role, and we do it computationally. So therefore, yeah.
Okay, sorry, Swagata, for interrupting. We are
Yeah,
past 1 hour. Could you please hurry a bit?
yeah. So therefore, I will show you some. So this is our main idea here. So study the detailed dynamics of the STWF for a non-parallel equilibrium mean flow that quantify the later stages of the nonlinear growth rates of the wavefront, capture accurately the bypass route of transition for the large excitation amplitude cases, the roots of 3D transition by the STWF for K and H type route of transition. And so I will describe it as I basically go along. So we take, this is our computational domain. This is for the 2D receptivity analysis, and this is for the 3D receptivity analysis. So we are basically reporting it here, essentially the 2D as well as the 3D receptivity analysis here. So from the wall segment, we give a particular excitation by imposing the wall normal velocity, and we are using the blowing suction exciter strip as you can see from this particular animation. And for the 3D excitation, for the 3D flow, our computational domain is something like this. We have an inflow plane, we have an outflow plane, we have both the planes where we use basically the periodic boundary condition, and then we use a definitive excitation. So we either use the Gaussian circular patch exciter or you use basically the span-wise strip exciter. So both the types of excitations are there. I will basically show you the result one by one. So one USP, or the one unique selling point of our simulation, is that with respect to the previous studies, we have taken a very large domain, and we have also purposely included the sharp leading edge of the flat plate. As you know, that sharp leading edge of the flat plate, there the boundary layer assumption breaks down, and therefore it can also act as a source of the growth of the disturbances. So we have taken, for the 2D analysis as well as for the 3D analysis, we have taken a very large computational domain, and if I compare it with respect to a similar analysis performed by Phys and Konzelman way back in 1990, and there the main purpose is to characterize the TS wave packet only, but here our main purpose is to find out the entire dynamics of the spatio-temporal wavefront. So therefore we have taken a very large computational domain. So with respect to the RA delta star, the outflow is located something around RA delta star is equal to 6,000 for the 2D case. For the 3D case as well, though we had the computational constraint, we had the resource constant, but still we have taken a very large computational domain in the streamwise direction. And if I compare it with the corresponding effort by the Stanford group by Sayedi, Hamman and Moin, published in 2013, so their computational domain has been shown here by this dotted line. So as you can see, with respect to their effort, our computational domain is quite larger. Okay, so we have, so this is our numerical formulation. You can read it from the slide. I will also share it the slide if you want. So we have used the stream function vorticity formulation for the 2D case, because the stream function vorticity formulation is inherently much more accurate from than the corresponding primitive variable formulation. Okay, so so here I am noting you the domain size and our Reynolds number based on the non-dimensional, basically the length scale L is 10 to the power 5, where L is essentially the 25 times the delta star, where delta star is the we have taken 4,500 points along the x direction and 400 points along the y direction. And we have used the OUCST scheme. This is essentially a compact scheme, a high accuracy compact scheme for the discretization of the compactive terms. The diffusive terms we have discretized by using the optimized staggered compact scheme twice, and time integration has been performed by the optimized Runge-Kutta schemes, and we have chosen these numerical schemes based on their superior accuracy in terms of preserving the numerical dispersion properties, which we have actually you can find out the phase error, dispersion error, and the numerical amplification error, and the error due to extreme spurious dispersion, or basically the QX. So we have tried to minimize all the errors in our numerical simulation by carefully choosing the time step, the time integration scheme, the spatial discretization scheme for the convective as well as the diffusive terms. And also for an accurate solution, we also have to get rid of the aliasing error, and for that purpose, and this aliasing error is significant during the during the later stages, the later nonlinear stages of the disturbance evolution, and we have used some for this purpose we have used multidimensional adaptive filters. Okay. So all of you, if you are interested in the details of the numerical scheme, you can visit the references or you can contact me. I will be happy to assist you. So here we are showing you a typical disturbance from the nonlinear Navier-Stokes simulation, and the disturbance frequency. So we always denote it by this non-dimensional frequency f, where f I have already defined. So here the frequency, this frequency is quite higher. So this line does not actually intersect the neutral curve, and you have the local solution, asymptotic solution, and spatio-temporal wave packet. The spatio-temporal wave packet, and as you do the Fourier transform, you also get the severe peaks, and say from this peak A, you can see the peak A corresponding to the STWF, and the other peaks are basically this asymptotic solution as well as the local solution, and they are super harmonics. Okay, now here I will show you an animation here of an 2D simulation. The exciter is located here. I'm showing you the disturbance u velocity plotting as a function of the streamwise coordinate x at a particular height, which is 0.8 times the, So this is the 0.8 times the displacement thickness. So here, as you can see, here is the exciter. So this is the asymptotic wave packet solution, and you can see some sort of spatio-temporal wavefront. Beyond this line also, there was spatio-temporal wavefront, or actually came from this asymptotic part, but it was so small that you cannot actually identify it. Now you can see that the spatio-temporal wavefront is growing, and as it grows, it ultimately breaks down and cause some sort of very sort of chaotic oscillations, and which you can identify with the transition of the flow. And here, here I am showing you the spectral variation. So this is the Fourier amplitude plotted as a function of the wave number for different time instants, and you can see the asymptotic part of the solution remains almost fixed. The wave number remains fixed, but as the time progresses, the spatio-temporal wavefront wave number gradually shifts from this particular point to a lower wave number component. And during the nonlinear stages, if you see the animation again, so during the nonlinear stages, see, this is basically moving from a higher wave number to a lower wave number part, and then it induces the higher harmonics because of the nonlinear interaction, and finally we'll get a continuous spectra because of this breakdown. Okay, so therefore you can see that the asymptotic wave packet remains spatially stationary, whereas the STWF grows in space and time, and therefore the STWF determines the dynamics and not the asymptotic part of the solution. So here we are categorizing the various growth stages of the STWF: stage 1, stage 2, 3, 4, 5, 6. The first part, the amplitude is decaying due to the nonlinear dispersion. The amplitude is decaying due to the linear dispersion, and the second phase is the linear amplification part, and the third part, the linear amplification growth rate is moderated because of the self and multimodal interactions. Okay, and then the higher order nonlinear instabilities, secondary instabilities basically kick in the stage 4, and leading to some kind of nonlinear saturation, and ultimately some sort of highly unsteady chaotic signal is obtained in the stage 6. So, however, that scenario is completely different. So this was for this was for a frequency of 1 into 10⁻⁴. So the non-dimensional frequency is 1 to 10 to the power minus 4. So suppose the non-dimensional frequency is lower. So here we are considering a lower non-dimensional frequency, and the excitation amplitude is 0.2% of the phase stream speed, so it's very small. And here you can see the transition scenario is completely different. So here again our exciter is located here. This is the near field solution or the asymptotic part of the solution, and as you can see, yeah, you can see the spatio-temporal wavefront because of the impulsive onset of the excitation, and with time progresses, like the previous case, it is also growing. It is inducing some secondary wave packet, but at later times, for this lower frequency excitation cases, basically the near field solution of the asymptotic part of the solution also exhibits some kind of spatio-temporal evolution, and therefore you get a continuous transition for this particular case, even if the flow is 2D in nature. And there, if you increase the amplitude from 0.2% to 0.3%, a slight increase, the situation is slightly more different. And here you can see both the spatio-temporal wavefront and the near field part of the solution remains attached all the time, and it is these two part which basically exhibits some kind of spatio-temporal growth, and which breaks down at later stages and issues some basically exhibits some kind of spatio-temporal growth and some kind of spatio-temporal background, basically breakdown, leading to highly unsteady flow and highly basically the chaotic flow. And when you analyze this kind of flow, we saw the footprints of 2D turbulence, basically with respect to the theory by Krishnan, where the spectrum should follow as k to the power minus 3. We basically saw this kind of footprint in this highly unsteady or this chaotic part of the solution after the breakdown has taken place. And then here we try to categorize our solution in the RE beta naught plane, and this figure has been taken from the in-depth thesis of Akhil. And for the different excitation, so this is all for the impulsive onset case. This is all for the impulsive onset case. The similar study has also been done for when the excitation onset is not impulsive, excitation onset is gradual. I will only show you a typical result for the 3D case, but for the excitation onset is gradual, we have for those cases also we have shown that it is the spatio-temporal wavefront which is the ultimate determinant of the flow transition process. Now here, this is the neutral curve, and these dots are essentially the says what is the exciter location and at which frequency the excitation has been performed. And depending upon the exciter location and the excitation frequency, we can have essentially 1, 2, 3, 4, 5, these 6 classes of evolution of the disturbance, where in the class A, for these black dots, when the exciter is located far above the neutral curve or far below the neutral curve, the STWP for the spatio-temporal wavefront decays, its amplitude decays with respect to time. And these red square blocks are where it is the TS wave remains stationary close to the exciter, whereas it is the spatio-temporal wavefront which basically grows, and ultimately the breakdown takes place because of the growth of this STWF and not the asymptotic part of the solution. And then we have the other dots, basically these triangular parts, where it is the kind of scenario which I just observed, which I just basically showed you for the lower frequency case, where it is the basically the interacting case where both the STWF and the near field part of the solution interacts with each other. So we have in the parametric space, and you can see this picture is completely, you cannot correlate this picture with the spatial stability analysis. You cannot correlate this picture with the spatial stability analysis, which essentially says that the flow is spatially unstable within this neutral curve. So no, it is not exactly true. So therefore, this is the finding. This is the saying that the spatio-temporal receptivity or the not only the spatio-temporal wavefront is the prime mover for the flow breakdown or the flow transition, but it is this breakdown which is basically determining the actual flow transition process. So
Swagata, I have a small doubt. So can I ask? Sorry to interrupt you.
yeah, sure.
So actually, just in the previous slide, you showed that there is small increase in the excitation amplitude from 2.2 to 0.3%. So you have got some different kind of attached signature. So why it is happening? Any physical explanation?
Why it is happening? Maybe that particular amplitude might be some kind of bifurcation amplitude. So if you know in the nonlinear dynamics, so this is basically the nonlinear. We are solving the nonlinear Navier-Stokes equation. So maybe that if the amplitude, there might be some kind of bifurcation amplitude. If the amplitude is smaller than that, you are getting this particular scenario. The amplitude is higher than that, you are getting this particular scenario. Okay, so this is all I think because of the
nonlinearities. Yes.
Yeah. So now,
thank you. Understood.
Yeah. So now from here we'll move from the 2D route to the 3D route. We have also done some 3D simulations because it is difficult to publish papers just by doing some sort of 2D simulation. So in the 3D simulations, so this is a typical picture. I have taken this picture from the well-known paper by Kachanov in the Annual Review of Fluid Mechanics in 1994. So that basically depicts the experiment performed by Klebanov, Tidstrom, and Sargent way back in 1962, where they placed some sort of spacers on the flat plate boundary and they excited it, some kind of ribbons. Okay, and then excited the boundary layer and they observed some kind of undulations, some kind of span-wise variations. Peaks, they termed it as peaks and valleys, and in some particular locations downstream, the high frequency oscillations were noted, and these high frequency oscillations intensified, leading to the transition of the flow field. Okay, so this is generally noted as the classical K-type route of transition. So K represents the Klebanov. Okay, Klebanov was a well-known fluid dynamicist. He has a huge contribution in the transition research. And then subsequently, people also investigated and tried to find out the routes of transition by the Klebanov route as well as the Herbert type route. So K-type route or the H-type route. So what they basically noted, when there is a certain fixed frequency excitation for certain scenarios in the transitional zone, some kind of lambda vortices are formed, and for the K-type route of the transition was noted when the lambda vortices are basically aligned. So I have taken this to schematic figure from the paper by Bill Sarek, published in 1989. Okay, so when the lambda vortices are aligned, so this K-type transition was noted to take place. And for certain excitation cases, I will show you when people have also noted that the lambda type vortices are basically staggered. They are arranged in a staggered fashion. So that has been termed as the H-type route of transition, and that has been explained via the resonant triad interaction mechanism of Craig, which was published in the JFM 1971. So the numerical simulation have been reported in SIAD as well as the distant puzzle, and the K-type transition has been noted when there is a 2D there is a 2D monochromatic excitation, and that has been mixed with a 3D excitation, but the frequency being the same. So both 2D and 3D monochromatic excitation, which has only one fundamental frequency, but they have not talked about the spatio-temporal wavefront. So this point has to be emphasized. So they are talking about the asymptotic part of the solution. They are all talking about the TS wave part of the solution. And when there is a 2D fundamental excitation, and that has been mixed with a 3D subharmonic excitation. So if the excitation frequency is F, the subharmonic means the excitation frequency is F by 2. So in that case, people observe this staggered arrangement of these vortices, and that has been termed as the H-type route of transition. But here again, I want to emphasize that they have not considered how the excitation has been onset, whether it is impulsive, whether it is gradual, and by what is the dynamics of the transient, what is the dynamics of the spatio-temporal effect. No, there the transition is happening only because of the amplification of the asymptotic part of the solution only. Okay, so far both K and H type roots of transition has been reported only for the asymptotic part of the solution. For H type, the fundamental frequency along with its subharmonic has been excited. Okay, so to simulate that, to simulate a similar problem, we have gone from the 2D simulation to the 3D simulations, and in the 3D simulation, we have used the velocity vorticity formulation because we cannot use the stream function vorticity formulation because the stream function is not actually defined for the 3D flows. Of course, its counterpart, the vector potential, can be defined, but we have gone to the velocity vorticity formulation. Okay, so this is the velocity vorticity formulation governing equation. This is the vorticity transport equation. It has the convective vortex stretching as well as the diffusive part, and when you update the vorticity, the attendant velocity can be found by solving the corresponding Poisson equation. But here we have solved this Poisson equation only for the two components of velocity. For the third component of velocity, since this is an external flow, we can take care of directly the continuity equation del dot v is equal to 0, and that can be directly integrated to find out the wall normal component of velocity. And if you are more interested, you can either contact me or this have been reported in these corresponding publications. Okay, and these are the numerical methods. These are all given here. Again, we have used an staggered compact scheme, optimized staggered compact scheme, which has been optimized to minimize the numerical sources of error. And we have used a staggered arrangement of variables, so the vorticity components and the velocity components are defined here. And we have used basically 2,500 points along the x direction, 300 points along the wall normal direction, and 51 points along the span-wise direction. In the recent simulations, we are also trying to increase that number of points. And high-order Perry type filters has been used for de-aliasing. Optimized Runge-Kutta scheme has been used for the time integration part. And here I am showing you a simulation for a Gaussian circular patch. Okay, so here, mind it, so there are basically here disturbance u velocity has been shown at a particular height. So at a particular height of 0.4 of the displacement thickness at the outflow, the excitation frequency is 0.5 10 to the power minus 4. So the exciter is located only at a particular patch here. Okay. And as you can see, you have the near field solution and you have the spatio-temporally evolving solution part of the solution. And we have the periodic, since we have imposed the periodic condition, so this means we have an exciter here, we have an exciter again also here, again we also have an exciter here. So as you can see, with later times, it is only the spatio-temporally moving wavefront, which basically grows in time, which basically grows in both space and time. And since we have this, we have the periodic condition, so the subsequent signals basically interact with each other. Subsequent signals basically interact with each other, and at a later time, you can get the footprint of turbulence. You can get the footprint of breakdown. This laminar flow basically breaks down. The higher order instabilities of the other breakdown takes place, and finally the transition from the laminar to this turbulent stage is happening for this particular excitation scenario. Okay, now here we are trying to show you the animation for three different excitation frequency case. The exciter is here, as you can see here. So this is basically a top view. This is basically a top view, as you can see, for the higher frequency of excitation case. So this is the STWP part. This is the spatio-temporal wavefront part, and you can see this spatio-temporal wavefront is basically its amplitude is growing as it is growing. So there is breakdown. The high wave number oscillations are induced not only along the central line but at the edge of the computational domain where the periodic condition has been imposed. So we have also performed with a larger domain along the span-wise direction. So there for those cases the breakdown essentially takes place the break because of the breakdown at the center line. Okay, so this is, so one thing has to be noted is that for the lower frequency excitation case, so there is a connection. There is a, so similar to the case we have noted for the 2D case, here also the spatio-temporal wavefront and the asymptotic part of the solution, or basically the TS part of the solution, which is wedge shaped for this particular case, remains a sort of connected. Okay, when the excitation frequency is lower. So when the excitation frequency is lower, there is some sort of interaction between the spatio-temporal wavefront and the asymptotic part of the solution, whereas that interaction is very weaker or almost absent when the excitation frequency is higher. Okay, and with this, we will move to the span-wise modulated excitation case, and this particular case has been chosen to mimic the experiments of the Klebanov et al., where they have excited the flow by some kind of specific exciters, span-wise modulated exciters. So we have also done a similar study. So we have done the span-wise modulated excitation here, and we have chosen the non-dimensional frequency to be 1, and also we report the case for f is equal to 0.5 into 10 to the power minus 4. Okay, and the alpha 1, which is basically the amplitude control parameter, is 0.01. So that means the excitation amplitude is 0.1. I think the 1% of the free stream speed. So here I am showing you for one such excitation frequency how the disturbances are evolving. As you can see, the exciter is here, the free stream flow is here. So here the disturbance u velocity has been plotted at a particular height and as a function of x, the streamwise coordinate x and the spanwise coordinate z here. And you can see the, here basically it is the growth of the spatio-temporal wavefront, and when the breakdown takes place, the downstream part remains almost stationary. It is almost fixed. So for this 3D case, the upstream transition location remains almost fixed once the breakdown essentially takes place. Okay, so now again here we have tracked the amplitude variation with respect to time. We can have the multiple stages of the growth of the amplitude. The stage 1, the linear exponential growth. Then again the sub-transition stage where the nonlinear self or the multimodal interaction happens. Then stage 3 where the secondary or higher order instabilities takes place. And then finally the spot formation due to turbulence. Okay, and then we try to quantify this transition process by plotting the parameters, basically the displacement and the momentum thickness. So here in the left slide, we are plotting the displacement and the momentum thickness at various time instants. And here we are plotting the shape factor. So shape factor is the displacement thickness by the momentum thickness. Okay, and as you know, for a laminar boundary layer, the shape factor has to be 2.59, and for a fully developed turbulent boundary layer, if it follows a logarithmic profile, so in that case the shape factor from that analogy it comes out to be 1.4. So this is the line. The first line is due to the laminar part. The bottom line is due to the fully developed turbulent wall-bounded turbulent shear layer. And as you can see, there is a transition from the laminar to the turbulent stage. And the upstream part remains almost stationary, whereas the downstream part propagates as the spatio-temporal wavefront basically moves downstream. Okay, so this is one of the scenario due to the impulsive onset of the excitation. And if you compare the compensated spectral density, there is a large part where it follows a k to the power minus 5/3 pattern, which is basically shows that a signature of the formation of the turbulence. So this is for the streamwise velocity component, the energy density due to the streamwise velocity component, and similarly if we plot for the energy density for the wall-to-wall velocity components, so it follows a pattern. It basically grows and then decays. So it follows a pattern as similar to, I will not say exactly, it follows a pattern which similar to what has been noted in the experimental paper by Saddogi and Virabali, where they have basically found out the energy density for various components of the velocity as a function of the streamwise wave number kx. Okay, so they have noted that because of the inherent anisotropy as well as the inhomogeneity in the wall-bounded turbulent shear layer, the E22 or the energy density due to the wall normal velocity will basically start from a very low number and it will saturate. It will basically saturate at a particular value and then it will decay. So in our case, also it is following a similar trend. So we can see some kind of correlation. You can see some kind of correlation between the actual fully developed turbulent wall-bounded shear layer and what we are actually observing by the growth of the STWF. And here we have not added any sort of numerical artifice or the numerical noise to obtain this transitional flow. Okay, so this is a completely deterministic scenario where the transition is happening due to the growth of the STWF only. And Dr. Pushpender Sharma further tried to find out the mechanism of this transition process. So here is one such slide. I have taken it from his PhD defense. So here, if you take a particular flow field at t is equal to 65, and you eject some kind of tracer particle, so flow remains frozen with respect to time, and you can see if the particles are ejected close to the wall, then there is a sudden eruption in the transitional zone, and there are two kind of vortices. So as you can see, as you can see, it is basically go round and round in two opposite direction, clockwise as well as anti-clockwise. And whenever if you eject the tracer particles at a particular height, it basically comes down. So this is similar to what is the ejection and the entrainment mechanism of when the breakdown basically takes place, when the transition basically takes place from the laminar to the turbulent flow. Okay, so we are seeing the footprints of it. And then finally, we try to characterize it with respect to the lambda vortices. I remember I said of the lambda vortices, the staggered and the aligned pattern of the lambda vortices. So when the excitation frequency is 1 into 10 to the power minus 4, here I am showing you the lambda vortices in the transitional zone, and these are sort of aligned in nature. However, when the excitation frequency is lower, they are kind of staggered in nature. So this picture will be also cleared here. So you can see the lambda vortices, which has been identified by the lambda 2 criteria. You know, the lambda 2 criteria is used to identify the vortex structures. So here we have used the lambda 2 criteria to identify the vortex structures in the transitional boundary layer, and we see that these lambda vortices are staggered in nature. And also there are some, you can see the footprints of some intermediate structure which essentially elongates as the basically from the laminar unsteady part to the transitional part, as you can see. So here we are seeing both is kind of aligned as well as the staggered part, just depending upon the excitation of the frequency. We have not added any subharmonic or 3D part of the we have not given any basically, as it has been postulated in the actual theoretical explanation of the K and H type of root of the transition. So we have not added any 2D fundamental excitation and superimposed with a 3D excitation. No, we have not done it. And here the transition is by the STWF. The transition is by the evolving spatio-temporal wavefront. But still, we are getting this H-type route of transition. Both the H and the K-type route of transition, depending upon the excitation frequency. So this is a kind of a different observation, different finding with respect to the prevalent theoretical explanations. Okay, so now there is another difference with respect to the impulsive start, as you can see here. When the excitation frequency, so here I am showing you the picture for when the excitation frequency is 1 into 10 to the power minus 4 and this 0.5 into 10 to the power minus 4. So when the excitation frequency is lower, as you can see, the asymptotic part of the solution and the spatio-temporally evolving wavefront, so they remain kind of connected. They remain kind of attached. So this is again similar to what we noted for the 2D case. A similar set of observation is also noted here. Okay, so for the lower frequency case is basically interacting. It's interacting between the asymptotic part of the solution and the spatio-temporal wavefront kind of interacts with each other. Whereas for the higher frequency excitation case, the interaction is quite less, and for this particular case, for this particular chosen value of lambda 2, you can see there is a kind of space here where you might conclude that these are actually two separate or two distinct entities. Now you have done all this, presented all the results for the impulsive excitation case. You might ask what happens if the excitation is gradual. So to try to answer that case, here we are doing a case when the excitation is gradual. So it following an error function. So it is an impulsive onset here, and then you have a gradual excitation onset. So so we have used this mathematical function, which basically consists of the error function, and we have this parameter alpha e. So if alpha e is very small, so it is a kind of an impulsive start. So we have basically computed three cases. We have the impulsive start, the near impulsive start when the alpha e value is very small, and the smooth start when the alpha e value is quite larger. And we can also compute it for a even larger case, but the specific finding has been plotted here for all the three cases, and the frequency is 1 into 10 to the power minus 4. So it is the higher frequency case, and for all the cases you can see that the spatio-temporal wavefront is there, and it is only the growth of the spatio-temporal wavefront which basically essentially determines the subsequent transition process. However, if the excitation onset is gradual, what happens is that the evolution of the spatio-temporal wavefront is slightly delayed. So only that effect, except that effect, we have not seen any other difference whether the flow excitation is impulsive or non-impulsive or gradual. So even for the gradual excitation onset case, it is the spatio-temporal wavefront which essentially determines the transition from the laminar to the turbulent state for this particular excitation cases. So this is all about I had to present. So right now we are also trying to find out. We are writing a proposal, and we are trying to characterize the generated turbulent flow vis-a-vis with respect to its statistics, with respect to its the anisotropy and the inhomogeneity, as well as the other energy budgets. Okay, so these are some kind of other future targets, and a book on the same thing, particularly from my PhD thesis, has been published here. So if any of you are interested, you can kindly contact me, or I will also share you all the slides. And thank you for your kind patience. I have taken a slightly more time, but I hope you.
No, that's absolutely fine. It was a very nice talk. Thank you for the talk. And the floor is now open for questions. Or any of you in the audience can unmute yourself and can ask the question. Yeah. So just to start with, I will ask some novice questions. Probably I don't know how much valid these questions are. Like, did you find all these transitions like prior to turbulence or on the start of turbulence to be deterministic? I mean, because you use the term pseudo-random. So can you elaborate?
No, so the pseudo-random term I use because so basically there are essentially two approaches to find out, I think, to characterize the turbulent flow. One is the statistical approach, where you measure the flow quantities and try to find out the statistics of it. So statistics essentially assumes that the numbers are basically random in nature. But my idea is that since all these fluctuations essentially obey the Navier stokes equation, so you cannot say that these are basically the random fluctuations.
Exactly.
Okay, so one fluctuation is basically governed by whatever is happening, say, sometime ahead. So therefore, I use this term pseudo-random. So they might appear like a random, but actually they might not be the. I mean, they are not actually random, right? If they had they been
Yes,
random,
so
they would
they
not
are
have
just
been.
higher order chaos, right? If I am correct.
Yeah. Right.
Yeah, that is a confusion because in turbulence everybody mixes this term chaos and randomness. I mean, it's very confusing
Yeah.
to me. Yeah.
So, so obviously they has to satisfy the equations. They have to satisfy the governing equations, basically the nonlinear governing equations. So yeah, so we cannot say that they are just random. I mean, if you say that they are random like that, one number does not have any any sort of correlation with the other, but they have a correlation. They have.
Yes, true. So, in most of these wall-bounded turbulent flows, we sometimes see the existence of intermittency, right? Before, like
Uh,
intermittently, the patches of turbulence comes up. So,
uh,
did you observe any such intermittent transition in the turbulence part?
uh, uh, we have actually maybe we have noted here yeah I mean uh, uh, maybe we have noted here I mean basically in the transitional part
Okay,
uh,
I see.
so we have to plot the time series uh, I
Yeah,
mean
sure.
much,
Fine. Yeah, okay. Another, it's a very general question. Like this spatio-temporal receptivity analysis, it seems very interesting. But in what way it is superior to other stability analysis method like Floquet you mentioned, or let's say dynamic mode decomposition or POD techniques? Like,
So
uh,
here the difference is that here basically the stability analysis is only concerned about the base flow. You do not consider what kind of excitation you are giving to the base flow. But here we are showing a case when depending upon the excitation, you can adopt various routes of transition.
yes, okay, right.
Right. So depending upon, so here we are not considering, we are not going via the stability approach. We are not having a boundary layer and we are not determining only the stability and we are saying, okay, okay, basically these are the frequencies which are unstable and these are the frequencies which are stable. We are not saying that. We are giving a deterministic excitation. We are giving a deterministic excitation and we are trying to find out how the system behaves to that particular excitation. So this is the receptivity route. So there obviously the disturbance will grow or decay both in space and time. So therefore we call it the spatio-temporal receptivity.
Okay, I see. And in what one part you mentioned that like you have observed signatures of 2D turbulence, right? So like
Uh-huh.
I was wondering how did you characterize that? Like how did you distinguish that it is 2D turbulence?
So we distinguish that when we plotted the spectra here, say for example here when the breakdown took place when we plotted the spectra, so that the basically the energy spectra. The energy spectra that followed a k to the power minus 3 kind of variation in certain range of the wave number.
Oh,
And that is identified as the signature of 2D turbulence following the works of Krishnan et al. Okay, so they specified that, but obviously they are in their case that they considered the 2D turbulence uh, uh, to be homogeneous and isotropic and all other sorts of assumptions. Here we uh, we we neither have the homogeneous case, neither we have an isotropic case. But
oh.
since we basically got that part, we said that okay, so that there might be some kind of correlation.
And is there any interlinking between this 2D turbulent transition and the 3D turbulent transition, or they are completely different? Like,
No, people say actually in the atmospheric dynamics, people say whenever people plot basically the energy spectra, so they see the signature of both the 2D turbulence as well as the 3D turbulence as well. So it has been observed. If you are interested, I can give you the specific reference of
oh,
a
yeah,
paper. I
what
think
is
it was. published in Nature. So people particularly in the atmospheric dynamics, they have seen the footprints of 2D turbulence as well as 3D turbulence. So there was the part of the spectra which followed as k to the power minus 3, and the part of the spectra which followed as k to the power minus 5 by 3. So
Okay, I see. Yeah, that's all I noted. Some of the
yeah,
queries. I don't see any other questions also. Okay, there is a question. Any energy budget analysis in stage 3, 4, 5 to have more understanding of the mode interactions?
yeah,
How
that is a good
modes
idea.
actually look like?
Stage 2 and 3, the energy budget analysis. I mean, that actually we are basically planning to do now with some students, and particularly with respect to the after the turbulent flow is happening. Uh,
Okay. In
so
the stage 3, I mean after the stage 3. Right.
after the stage 3.
Okay. Okay. And also the last question maybe, is there any connection with hairpin growth from these mode interactions?
Hairpin growth and the mode interaction.
Probably the lambda vortices you showed. Probably the question is
Uh-huh.
related to that.
So here the idea was that oh sorry, the actually uh, I think if I showed you this show you this picture. Yeah, you can see these have a basically kind of two legs, and then these two legs basically join, and they have a kind of omega kind of vortex. And in the transitional zone, this top kinds of basically lifts up, it intensifies, and it breaks down, and basically in the subsequent location. So this is the connection as I think as I can see here.
Okay. And did you see the unstable modes for this? Like, did you do any kind of model decomposition to identify which modes are basically responsible for the turbulent transition?
Which no, we have done basically tried to identify with respect to the Fourier transform. We have
Yes.
done a detailed study. So we have found out various peaks, and we have tried to find out the dynamics of the frequency components, how they are growing, and their I mean the those kind of detailed analysis. Yeah, we have done for the 2D part. The 3D part also we have done a more or less similar. I
Okay.
mean, uh,
It's
so
really beautiful. Yeah.
yeah, yeah.
Thank you. Yeah,
Yeah.
if we don't have any other questions from the audience, I think again, thank you all for attending the talk and for your patience. It was really a nice talk. I think we can close the session here.
Yeah.
Thank you,
Thank
Swagata,
you.
again. Okay, so I'm closing the talk here. Thank you.
Yeah.
Thank you.